The study in mass spectrometry by using the mass spectrometer can determine the relative atomic mass of an element. When a mass spectrum is generated, we can find out the number of isotopes of an element and the relative abundance of the isotopes respectively.
Next, let us to have a quick look about the first chapter in Semester 1 STPM Chemistry. I hope this will help you.
Welcome to this video on atoms, molecules, and stoichiometry. We will begin by exploring the fundamentals of relative atomic, isotopic, and molecular masses. A mass spectrometer is a versatile instrument. It is used to determine the relative isotopic mass, the abundance of isotopes, relative atomic and molecular masses, and even the structural formulae of compounds. This diagram illustrates the core components of a mass spectrometer, including the ionization, acceleration, deflection, and detection chambers, all operating under a vacuum. In this process, a sample is ionized and accelerated as a beam. As the ions pass through a magnetic field, they are deflected based on their mass, allowing only specific ions to reach the detector. There are 5 essential processes in mass spectrometry: vaporization, ionization, acceleration, deflection, and detection. Step 1 is vaporization. The sample enters the vaporization chamber, where it is vaporized. If it's a volatile solid or liquid, it is preheated before moving to the ionization chamber. Step 2 is ionization. As the vapor enters the chamber, it is bombarded by highly energized electrons from a heated filament. These collisions knock electrons off the atoms or molecules, creating positive ions. Step 3 involves acceleration. A negative potential applied to plates creates an electric field that accelerates these positive ions. Step 4 is deflection. An electromagnet produces a magnetic field that deflects the positive ion beam in a circular path. The degree of deflection depends on the mass-to-charge ratio. Ions with a higher ratio are deflected less. Finally, step 5 is detection. The ions arrive at the collector successively. An amplifier and recorder then measure the relative abundances of these ions, represented by the height of the peaks. This visual shows how ions with different masses are separated within the magnetic field before reaching the detector. Next, we will examine the relative abundance of isotopes and how to calculate the relative atomic mass of an element using its mass spectrum. For a monoatomic element, the mass spectrum shows lines indicating isotopes. You can calculate the average atomic mass by summing the mass of each isotope multiplied by its abundance, divided by the total. For diatomic elements like chlorine, the spectrum shows peaks for both the atom and the molecule. The specific ratios, such as 9:6:1, are determined by the probability of different isotopic combinations. Finally, for compounds, the mass spectrum identifies both the molecular ion, which provides the molecular mass, and various fragment ions created as the molecule breaks down. The tallest peak is known as the base peak. Let's analyze the fragmentation pattern of ethanol in a mass spectrum. The peak at major spur Z45 comes from the loss of a hydrogen radical, while the IMDRA Z43 ion results from further loss of hydrogen gas. The M for Z31 ion represents the base peak, formed by splitting the CC bond. Moving on to the mole concept, a mole is defined as the amount of substance containing the same number of particles as 12 grams of carbon-12. This quantity is known as Avogadro's constant, which is 6.02 times 10 to the power of 23. This slide outlines calculations for various substances. We can determine moles using mass and molar mass, apply density formulas, or calculate the number of particles. For gases, we use molar volume constants or the ideal gas equation. Additionally, percentage yield helps measure the efficiency of chemical reactions. In this example, we calculate the empirical formula from combustion data. By determining the moles of carbon, hydrogen, and oxygen produced from a known mass of a compound, we can establish the simplest molar ratio between the elements, which in this case leads to the empirical formula C5H6O. Next, we look at identifying limiting and excess reactants. By comparing the moles of reactants against a balanced chemical equation, we can determine which reactant will be exhausted first. This limiting reactant dictates the maximum theoretical yield of the product, such as the titanium calculated here. Thank you for watching this video on atoms, molecules, and stoichiometry. We have covered mass spectrometry patterns, the mole concept, stoichiometric calculations, and how to work with limiting reactants.
Thanks for your attention. I hope this short brief may give you some ideas. What are the important things that you may learn through the whole topic?